There's two types of forces. Intramolecular forces, which is what our bonding unit is over. That's the forces within the molecule. Those are our covalent and ionic bonds. This is a covalent bond. Those do not break during phase changes for any of our examples. Intermolecular forces, which are abbreviated IMF, are the forces between molecules. So intra is within, inter is between, like an interstate goes between two states. So these attractions between these water molecules is hydrogen bonds. Those are what will break when water undergoes a phase change, such as boiling, and they'll weaken during melting. Intramolecular forces, ionic bonding, forms a lattice. So here we have our sodium and our chlorine. And there's an ionic bond between them. But notice there's also ionic bonds within and between. So for ionic, it's the same for the intra as the intermolecular force. That's why, as we see later in the units, ionic bonds ionic compounds have very high melting and boiling points because you're breaking an actual bond for an ionic compound to boil. The strength of an ionic bond depends on two things: the charge on the ions and the size of the ions. The higher the charge, the stronger the attraction. And the smaller the ions, the closer they're able to get to each other, making it a stronger attraction. So the higher the charge and the smaller the size. So in this case, we have magnesium chloride and aluminum chloride. Magnesium's a +2, chlorine's a -1, aluminum's a +3, and chlorine's a -1. 2 times 1 is 2, or the absolute value of 2 times 1 is 2. 3 times -1, absolute value is 3. Therefore, aluminum chloride has higher charges, making its ionic bond stronger than magnesium chloride. If we are comparing magnesium chloride versus magnesium bromide, they both have magnesium, so really we're just looking at the chlorines. Magnesium was a +2 and a -1, a +2 and a -1. Notice the charges are the same. If the charges are the same, you look at size. So charge comes first and then size. Because magnesiums are the same, we look at chlorine and bromine. We want the smaller ion. Size, if you recall, increases as you go left and down. So since bromine is larger, MgCl2 will have a stronger ionic attraction than magnesium bromide. So pause the video and figure these out on your own. Restart when you have your answers. Alright, so checking your answers, A, you should have got an FeCl3 because it had the higher charge. B, you should have got lithium oxide because the charges are the same, so we were looking at size, and lithium is smaller than cesium. For C, you should have got magnesium sulfide because when you multiply the charges, we get a 4 and a 3, and magnesium sulfide has a higher charge. And for the last one, KBr and KF, you should have gotten KF because fluorine is smaller than bromine. Covalent bonds, all of our lines where they're sharing electrons, all those are covalent bonds. Again, those do not break during phase changes. Our intermolecular forces are the attractions between the two molecules. There's 5 types of intermolecular forces that we'll be talking about. These are listed in your notes, and we'll be going over those. So the first one is the ion dipole force. It's an interaction between ions and molecules with a permanent dipole. In other words, between an ionic compound and a polar molecule. So in our example, we have sodium chloride and water. When salt dissolves in water, the sodium and the chlorine ions separate and are surrounded by water. Recall that water has a slightly negative oxygen and slightly positive hydrogen. Because sodium is positive, all of the water surrounding it have oxygen facing the sodium because opposites attract. And if we look at our chlorine molecule, which is negative, all of the hydrogens are facing towards the chlorine because slightly positive is attracted to the negative. Because those ions are surrounded by water, they're not able to go back together. The strength of an ion dipole force depends on 3 things. The distance between the ion and the dipole. The closer they are, the stronger the attraction. Therefore, we want smaller ions and atoms. The charge on the ion. Just like in our ionic compound, the greater the charge, the greater that attraction will be. So higher charged ions. And the magnitude of the dipole. Magnitude of the dipole is simply saying how polar is that bond. The greater the magnitude of the dipole, the stronger the attraction. And remember, the more polar the bond, the greater the electronegativity difference. With a dipole-dipole force, those are the interactions between molecules with a dipole. In other words, 2 polar molecules. They can be the same polar molecule or different polar molecules, but it's between 2 polar molecules. Recall that when you have a polar molecule, one side is slightly positive and one side is slightly negative. Therefore, we have attractions between the molecules on their slightly positive and slightly negative, and we also have some repulsions between our negatives and positives, which keep them from getting too close. So because we have slightly positive, slightly negatives, the end of one molecule is attracted to the negative end of the other molecule. The strength of a dipole depends on 2 things. The distance between the molecules. So again, the smaller the molecule, the stronger the attraction. And again, the magnitude of the dipole. So just as we saw an ion dipole, the stronger the electronegativity difference, or the larger the electronegativity difference, the greater the magnitude of the dipole. So if they're similar in size and mass, we're going to look to see which ones have the greatest electronegativity difference. So our example problem, HCl and HBr, both of these are polar molecules, so they both exhibit dipole-dipole forces. We know they're both polar because there's 2 atoms, and they're not the same atom. So the electronegativity difference, more than likely, is going to be more than 0.4. So if I'm trying to find out which dipole-dipole force is stronger, first I'm going to look at the size. Out of HCl and HBr, HCl is much smaller than HBr. So chlorine is smaller than bromine. According to number 1, the smaller the molecule, the stronger the attraction. So HCl has a greater dipole force than HBr. Hydrogen bonding is an extreme form of dipole-dipole interactions. where one atom involved is always hydrogen, and the other atom is a highly electronegative nitrogen, oxygen, or fluorine, or NOF on the periodic table. So on our pictures, we have a hydrogen from one molecule is attracted to an oxygen of another molecule. They're not bonded, they're just attracted. So although the word is hydrogen bonding, we're not making actual bonds. These are still attractions between molecules. And over here in our ethanol, so this is ethanol, and we have two waters attracted to it. So the hydrogen is attracted to this oxygen. So think about, is this that I just drew a hydrogen bond? It's between a hydrogen and oxygen. So think about why or why not that's a hydrogen bond. If you said it's not a hydrogen bond, you are correct. And it's because that hydrogen is attached to a carbon. This is not a polar bond. This hydrogen is not slightly positive. This hydrogen is slightly positive because this bond is polar. So we have a slightly positive hydrogen and a slightly negative oxygen attracted to a slightly negative oxygen. While this hydrogen is not slightly positive, there's going to be no attraction. So it's got to be a hydrogen attached to an NO or F, attracted to an NO or F in another molecule. The reason hydrogen bonds are such strong dipole-dipole interactions is the same reason that a dipole-dipole is strong. In order for a dipole-dipole to be strong, we wanted a large polarity difference. Well, NO and F are all very electronegative, leading to a very polar bond. Also, for dipole-dipole to be strong, we wanted small ions or small atoms. All H, N, O, and F are all very, very small, therefore strengthening that attraction. So a hydrogen bond is a special kind of dipole-dipole attraction because it's such a strong dipole-dipole. So it's in a separate category. Dipole-induced dipole is the interaction between a polar molecule and a nonpolar molecule. So over here we have oxygen, which is just nonpolar because the electrons would be shared equally between the two oxygens. But a molecule with a permanent dipole, which is a polar molecule, can induce or create a dipole in molecules that don't have that permanent dipole, such as nonpolar molecules. So water is slightly positive and slightly negative. When this slightly negative oxygen comes close to oxygen, all of oxygen's electrons start going towards the left-hand oxygen, making this side slightly negative and this side slightly positive. So then we have some attraction, which then induces the next one. All the electrons will then go over to this side, making this side slightly positive and this side slightly negative. So because I have a polar molecule coming in contact with a nonpolar molecule, this slightly negative repels the electrons, making one side slightly positive and the other slightly negative. The final type is London dispersion forces, and this is the interaction between nonpolar molecules. London dispersion forces are important because if these didn't exist, substances such as noble gases would never be able to liquefy or solidify. Because in order for a liquid or a solid to form, there has to be attractions between the molecules. Because as we saw from your activity, gases don't have attractions. They're too far away from each other to have those attractions. So the basis of London dispersion forces are the electrons are always moving. So the electrons are moving around, and they stay relatively equal on both sides. But occasionally, one side gets more electrons than the other side as they're moving around, which causes a momentary dipole or instantaneous dipole, meaning that it doesn't last forever and it just happens due to the movement of electrons. So one side becomes slightly negative, the other side slightly positive, due to the electrons not being evenly distributed. This then causes or induces a dipole on the neighboring atom, because when I have this slightly positive, all the electrons in this atom, or more of the electrons, will be like, oh, I want to be on that side then, because that side's positive and they're attracted to it. And I have fewer on the other side, making this side slightly negative and slightly positive, which then can induce a neighboring atom and so on and so on. So looking at our example problem, we have helium and xenon. Helium only has 2 electrons, while xenon has 54. Remember, you get your number of electrons from the atomic number. We're not looking at valence electrons, so we're not saying xenon has 8. We're looking at the total number of electrons. So which one, helium or xenon, do you think is more likely to have one of these momentary dipoles, where the electrons are not evenly distributed? Something that has 2 electrons, or something that has 54 electrons? If you said something that has 54, you're correct, because if you only have 2, there's a good chance they're going to stay on opposite sides of the nucleus. While if you have 54, there's a better chance that you're not going to have exactly half on both sides, and you're going to wind up with one side that has more than the other, causing a dipole. So xenon has a greater London dispersion force than helium, because there's only one factor that determines strength for London, and that's number of electrons. The more electrons in an atom or molecule, the greater its ability to exhibit a momentary dipole or become polarizable. And again, make sure you're looking at total number of electrons. People mess up on this one a lot because they look at valence electrons. So for example, if I was looking at CCl4 versus CBr4, these are both nonpolar, so they both have London dispersion forces as their intermolecular force. If you were looking at valence electrons, you would be like, oh, well, they both have 32, so they must be equal. But that's not correct, because bromine has many more electrons than chlorine does. Therefore, CBr4 would have stronger London attractions than CCl4. So it's hard to keep all of these different IMFs in your head and identify which type is which. So open your notes to the middle section where you have that blank page. So go ahead and draw this concept map. Real quick, let's go through your concept map. It says first, do you have an ionic compound? If yes, then you ask yourself, well, do you have polar molecules and ions present? Or do you have a polar molecule and ionic compound present? If no, it's just ionic bonding. If yes, it's ion dipole forces. If there wasn't an ionic compound, then you say, well, do you have polar molecules involved? If no, then it's London dispersion forces, because that's the only type that's in nonpolar. If yes, you do have polar molecules, you need to ask yourself, well, do you have polar and nonpolar compounds? If yes, then it's dipole-induced dipole. If no, you ask yourself, well, do you have hydrogen atoms bonded to N, O, or F? If no, it's just dipole-dipole. And if yes, it's hydrogen bonds. So pause the video and draw this concept map. Make sure you draw it neatly, because you're going to be referring back to this on your homeworks, making sure that you get these questions down. Because on the test, you won't have this concept map, and you'll want to make sure that you can ask yourself these questions to identify your IMF correctly. One last thing, these are the strongest to the weakest. There are some overlap and some exceptions to that, but without more data, this is the order that we go with. Okay, underneath each of these, we're going to go ahead and add some more information so you have it all in one spot. Underneath the ionic bonding box, so underneath this box, write higher charge and smaller size. If you're comparing two ionic compounds, you're going to want to look for the one that has the higher charge, and if they have the same charges, you're looking for the smaller size. Underneath ion dipole forces, write must have two different molecules, ionic and polar. It has to be two different molecules. Hydrogen bonding, you don't have to write anything underneath it. Dipole forces, write small size, high electronegativity. And remember that electronegativity increases as you go up and to the right. For dipole-induced dipole, you must again have two different molecules. In this case, a polar and a nonpolar molecule. And under London dispersion forces, if I'm comparing two different London dispersion forces, I'm going to look to see who has the most electrons. That's going to have the stronger London force. So if I don't have two different molecules, there's no way it's ion dipole or dipole-induced dipole. Once you've written this down, then restart the video. Pause it if you're not done. So here we have some practice problems. We're going to identify what type of IMF is in each of these. Again, our choices are these at the bottom: ionic bonding, ion dipole, hydrogen bonding, dipole-dipole, dipole-induced dipole, or London dispersion forces. For abbreviations, London dispersion you can say is LDF, dipole-induced dipole, DID, dipole-dipole, DD, hydrogen bonding, HB, nothing for ion dipole, and ionic, you can just write ionic. So Fe2O3. First, we say, is there an ionic compound? Well, is there a metal? Yes. So then we say, well, do we have a polar molecule and ions present? Do you see Fe2O3 and something else? Or Fe2O3 in something else? No. In which case, we only have one substance. So that's ionic bonding. Next, we have CH4 is mixed with liquid bromine. So CH4 mixed with bromine. First, do we have an ionic compound? Neither of those have a metal, so no. Are either of those polar? So this one has the same thing all the way around, so it's nonpolar. This one has one bond, and that one bond is nonpolar, so nonpolar. So do we have polar molecules involved? No. So it's just London dispersion forces. Notice that they were different molecules, but they had the same force. So it's still London dispersion forces. CH2Cl2. Some of these you'll have to draw out. This one you don't have to draw out because looking at the formula, you know there's more than one atom attached to the central atom, making it polar. So first, is there an ionic compound? No, because there's no metal. Do you have polar molecules involved? Yes. Do you have a polar molecule and a nonpolar compound? No. Because again, it's not and something or in something. There's just one compound. Do I have hydrogen attached to N, O, or F? Nope. Therefore, it's dipole-dipole. Magnesium chloride is mixed with HF. So first, is there an ionic compound? Yes. Do I have polar molecules and ionic compounds present? Well, this one's ionic. This one is not ionic, and it's polar. So, yes. Then that means it's ion dipole. Notice I have two different substances, so I can have an ion dipole. H2SE. This one, technically, I don't need to draw it either because I know hydrogen can't double bond. So selenium must have lone pairs. And if you recall back from bonding, if you have lone pairs, then the structure has to be polar. So first, is there a metal? Nope. So it's not ionic. Do I have polar molecules involved? Yes. Do I have a polar and a nonpolar compound? No, because again, it's not and something else. Do I have hydrogen attached to N, O, or F? Nope. So it's dipole-dipole. And HCl is added to a solution of HBr. So first, is there an ionic compound? No, no metals. Do I have polar molecules involved? I have one bond, and that bond is not between the same element, so this one's polar. This one I have one bond, and that bond is polar because not the same element. So yes, I have polar molecules. Do I have polar and nonpolar? Nope, both polar. Do I have hydrogen attached to N, O, or F? Nope. So dipole-dipole again. You have these 6 to try on your own. Restart when you have an answer. For liquid oxygen, you should have got an E, or London Dispersion Forces. For 2, this one was nonpolar, this one was polar. So you should have gotten D, dipole-induced dipole. For 3, it's polar, so you should have gotten B, which is dipole-dipole. For 4, we have OH at the end. It's not ionic, therefore it's going to be C, hydrogen bond. 4, you have a nonpolar molecule, and so it's E, London Dispersion Forces. And 6, you had an ionic and a polar, so it should have been A, ion dipole. If you didn't get those, you need to come and ask in class. On this one, identify the type each of these have, which type of IMF, and then answer the question. Do any of these have 2 different molecules? Answer that is no, so it cannot be this one, and it can't be this one. So for A, if you didn't draw A out, you're going to miss problems on your test. You needed to know that it had a lone pair. You can't tell if A has a lone pair without drawing it out, because maybe it has double bonds on both sides, but in this case there was a lone pair, making it dipole-dipole. For B, we know that that one is London dispersion because it's nonpolar. Same thing all the way around, no lone pairs. C, you didn't need to draw out because you can easily see there's more than one atom attached to the central atom. So it's polar, and I don't have N, O, or F, so it's dipole-dipole. And D, I didn't need to draw that one out because hydrogen can't double bond, so there must be lone pairs on sulfur. But there's no N, O, or F, so it's just dipole-dipole. So the answer to the question is B. To answer this one, first we've got to figure out what type of IMF is in each of these. We just said that SO2 was dipole-dipole. Figure out the next two and then rank your molecules. Restart when you have an answer. So this one you should have got was H bond. And helium you should have gotten was London dispersion force. And since we want increasing IMF, we want weakest to strongest. LDF is the weakest, so helium is the weakest. Then dipole-dipole, and then hydrogen bonds, or A. Figure out which of these best represents hydrogen bonding in methanol. Restart when you have your answer. So A is incorrect because we have hydrogens attracted to hydrogens. And that's not how hydrogen bonding works. B looks good. There's an oxygen attracted to a hydrogen and an oxygen attracted to a hydrogen. But notice this hydrogen is attached to carbon and this hydrogen is attached to carbon. Therefore, B cannot be hydrogen bonding because this hydrogen is not slightly positive or slightly negative, nor is this one. C looks pretty good. We got a hydrogen that's attached to an oxygen, attracted to an oxygen. And D can't be right because, again, like A, we can't have hydrogens attracted to hydrogens. So last step. If we have HF and water, draw two hydrogen bonds between these. Restart when you have an answer. So first, hydrogen is slightly positive, fluorine slightly negative. Slightly positive, slightly negative, slightly positive, slightly positive, slightly negative. So this fluorine cannot be attracted to oxygen because they're both slightly negative. So this hydrogen is attracted to that fluorine. This oxygen is slightly negative. It's attracted to that hydrogen, which is slightly positive. So those are two places it could hydrogen bond.